Now we're going to take a look at potential energy and add it to our understanding of the law of conservation of energy. The two types of potential energy we're going to look at are gravitational potential energy and spring potential energy. Our aim in this and the next video will be able to reach these learning targets here. So make sure to pause the video before continuing and read through these. It'll also be a good idea to refer back to them at the conclusion of the video and when you're studying. Now, as we've already covered, work is done upon an object whenever a force acts upon it to cause it to be displaced. Work involves a force acting upon an object to cause a displacement. In all instances in which work is done, there is an object that supplies the force in order to do the work. For example, if a plow is displaced across a field, then some form of farm equipment, usually a tractor or a horse, supplies the force to do the work on the plow. If a barbell is displaced from ground level to a height above like a weightlifter's head, then the weightlifter is supplying a force to do the work on the barbell. In all instances, an object that possesses some form of energy supplies the force to do the work. In the instances described here, the objects doing the work possess like a chemical potential energy stored in food or fuel that is transformed into work. In the process of doing work, the object that is doing the work exchanges energy with the object upon which the work is done. When the work is done upon the object, that object gains energy. The energy acquired by the objects upon which work is done is known as mechanical energy. Mechanical energy is the energy that is possessed by an object due to its motion or due to its position. Mechanical energy can either be kinetic energy, which is the energy of motion, or potential energy, which is stored energy of position. Objects have mechanical energy if they are in motion and or if they are at some position relative to zero potential energy position. For example, a brick held at a vertical position above the ground, or zero, we call the ground the zero height position. So a brick held at a vertical position above the ground would have gravitational potential energy. A moving car possesses mechanical energy due to its motion. A moving baseball possesses mechanical energy due to both its high speed in the form of kinetic energy and its vertical position above the ground in the form of gravitational potential energy. A drawn bow possesses mechanical energy due to its stretched position. We call that elastic potential energy. So now we're going to move on and we're going to look at these different types of potential energy. So when two or more objects in a system interact, it is possible to store energy in that system in a way that the energy can be easily recovered. For example, the earth and a ball interact by the gravitational force between them. If the ball is lifted up into the air, energy is stored in that ball-earth system that can later be recovered as kinetic energy when the ball is released and falls. Similarly, if we push a box against a spring, energy is stored that can be recovered when the spring later pushes on the box. And this sort of stored energy is called potential energy, since it has the potential to be converted into other forms of energy, such as kinetic or thermal energy. Gravitational potential energy is stored when an object's height increases above a reference level, and elastic potential energy is stored when a spring is stretched or compressed. There are other forms of potential energy that we'll see in other units, but for now, we're just going to concern ourselves with just these two. Now, when we lift an object some height above a reference frame, work is done and the object gains potential energy. Doing the work on the object transfers that energy to the object. The energy it gains is equal to the work that's done on it. If the object is lifted at a constant velocity, then there's no change in the object's velocity, and so no change in the object's kinetic energy. In such a case, there would only be a change in the object's potential energy, and the amount of work done would be equal to that change. On the other hand, if the object's velocity does change during the lifting, then there would be a change in kinetic energy and gravitational potential energy. In such a case, the work done is equal to the sum of both changes in energy. The main point here is that the amount of work that is done is equal to the change in energy. This is our work energy theorem. And it applies to all forms of energy, potential, kinetic, thermal, all of that. Now, with gravitational potential energy, we have an expression, mgh. So this is the equation for gravitational potential energy, where ug is the potential energy, m is the mass of the object, g is the acceleration due to gravity, and h is the vertical displacement above some reference level. Now, an object that is lifted to some new position can, if it's released from that position, do work as it falls back down. So think of like a hydroelectric dam. The water behind the dam has a gravitational potential energy as it falls and does work on the turbines within the dam. The turbines turn and generate electrical energy, which is then conducted along metal wires to all those structures needing it. The net work done by a falling object is simply the change in potential energy. And we can now add this concept to our understanding of the work energy theorem and apply it to the law of conservation of energy. Now, it's going to be important for us to understand that gravitational potential energy depends only on the height of the object above a reference level and not on the object's horizontal position. Consider this 51 kilogram hiker. His gravitational potential energy depends only on his height above the ground. So it's the same at same value at any point on path A where he's at a height of 100 meters above the reference level. If he had instead taken path B, his gravitational potential energy at 100 meters would be the same 50 kilojoules. It doesn't matter how he gets to the 100 meters, his potential energy at that height will be the same. And now, this holds true for all potential energy. All potential energies depend only on the position of the object and not on the path the object took to get to that position. This fact is going to allow us to use the conservation of energy to easily solve a variety of problems that would be really difficult to solve using Newton's laws alone. So because we won't need to know the details of the path of the object, just its starting and ending points. So let's take a look at a couple of examples. So here we have a 12,500 kilogram boulder that's been lifted onto a 157 meter cliff, and we want to know the boulder's potential energy with respect to the ground, and then how much work was done to lift that boulder if it was lifted at a constant speed. So for part A, we start with our equation for gravitational potential energy. Putting in our mass, g, and the height above the reference level, we end up with an energy of 1.92 times 10 to the 7 joules. Now for part B, we want to know how much work was done to lift the boulder if it was lifted at a constant speed. So if it's lifted at a constant speed, its velocity is not changing, so we're not changing its kinetic energy as we lift it. We're only changing that potential energy, and because work is equal to the change in energy, then the amount of work that was done is the same 1.92 times 10 to the 7 joules. So let's look at another example. Here we are at the fair and we've got Katie trying to ride the water slide whose shape is shown. The starting point is 9 meters above the ground and she pushes off with an initial velocity of 2 meters per second. If the slide's frictionless, how fast will she be traveling at the bottom? So to begin here, we have to make a decision about what kinds of energy exist in each of these positions for her. Up here, she's got a gravitational potential energy, and she's got an initial velocity, which means she has some kinetic energy. Both of those are going to be changing as she comes to the bottom of the water slide. The gravitational potential energy is going to go to 0, and she's going to be left with only kinetic energy. Due to the law of conservation of energy, then, we can equate those two positions, the energies at those two positions, and we can say that when she has a gravitational potential plus the kinetic energy she starts with is going to equal all of the kinetic energy she ends with. Okay? So when we're working then with our expressions for each of those types of energy, we notice right away that we've got this mass involved, right? We don't know what Katie's mass is, it's not given to us, but from this we can see that the mass will end up canceling out on both sides there. So when we put in the value for our height, we put in our initial velocity here, and we pull out the masses, we end up with a velocity at the bottom of the water slide of 6.72 meters per second. We're going to next discuss spring potential energy, but before we do, we need to take a short side trip to discuss what's called Hooke's law. Hooke's law is one of those physics concepts that really could be inserted in several different areas. We could have covered it during Newton's laws, for example, but covering it here allows for a nice explanation of the derivation of the equation for spring potential energy. Basically, Hooke's law says that the amount of force that it takes to compress a spring is equal to the force that the compressed spring can exert back. It's characterized by this equation here, where that spring force is equal to the spring constant times the displacement of that spring. The spring constant, K, is a unique value for each spring. It has the units of newtons per meter. Basically, the spring constant means that for any given spring, it takes so many number of newtons to compress it 1 meter. So for a spring with a spring constant of 5 newtons per meter, it takes 5 newtons to compress the thing 1 meter. A spring with a spring constant of 50 newtons per meter would take 50 newtons to compress it 1 meter. So as you can see, a stiff spring would have a higher spring constant than a soft spring. The minus sign in Hooke's law simply means that the direction for the spring's force is opposite the direction of the force that's compressed it, that has compressed that spring. So which makes sense, right? If you compress a spring to the right, it's going to exert a force to the left. That's all that minus sign means. Your reading packet does a really nice job of explaining the derivation of the equation for spring potential energy. But because we want to spend time with example problems, I'm not going to go into it here. You should read it instead. So spring potential energy, or sometimes it's called elastic potential energy, is the energy that's stored up in a compressed spring or stretched elastic material. The equation for spring potential energy is 1/2 kx squared, where k is the spring constant of the spring and x is the displacement from equilibrium for that spring. So it's important to remember that this displacement is from an equilibrium position. We can find the equilibrium position of a spring by removing any mass from it and seeing where that spring naturally sits. That position would be the equilibrium position. So any problem-solving situation where a spring is stretched or compressed involves spring potential energy, which we can now look at some examples of. And we can add our spring potential energy to our understanding of the conservation of energy in any situation where we may have kinetic energy, gravitational potential, and spring potential. We would put in that equation for spring potential energy. So again, let's look at an example. So here we have a spring-loaded toy gun used to launch a 10-gram plastic ball. The spring has a spring constant of 10 newtons per meter. It's compressed by 10 centimeters as the ball is pushed into the barrel. When the trigger is pulled, the spring is released and the ball shoots back out. And we want to know the speed of the ball as it leaves the barrel. So in this position right here, we have all spring potential energy, and over here we'll have all kinetic energy. So what we can do, because of conservation of energy, is we can equate those two. The spring potential will equal the kinetic energy. We have 1/2 kx squared on one side and 1/2 mv squared on the other side. So difference between using gravitational potential energy and kinetic energy and using spring potential and kinetic energy is we cannot cancel out this mass. The mass, we have to know the mass of the object that we're working with. So when we go to plug in our values, we have to make sure and be careful to convert our compression from the 10 centimeters into meters, so it's a 0.1 meters, and our mass has got to be in kilograms. Okay, so that's something we've always got to do, is convert any distances into meters and any masses into kilograms. And once that's done, we plug in our values and we get a velocity out of the gun of 3.16 meters per second. Now, one thing also to kind of keep in mind, as we imagine this kind of situation, say if this gun were being fired from some height, we're given a height and said, let's say whatever it is, 5 meters, okay? We would have to then, in that case, and we wanted to know, say, the velocity right before it hits the ground or something, we would have to include in our initial case that gravitational potential energy, and then we could just connect those two from there. All right, so this is going to conclude our discussion of potential energy. One other thing to pay attention to will be the discussion of thermal energy in your reading packet. We'll cover thermal energy more completely in our unit on thermodynamics, but in the reading packet, that's a good introduction to thermal energy. And it's a good possibility of seeing probably one question or so on a test dealing with that thermal energy stuff. Okay, so see you in class.